welcome address, and then we can go ahead with your presentation, sir.
Sure.
A very warm evening to one and all present here in this special gathering. We come to the last session of the ATAL online FTP on revolutionizing electric vehicle powertrains, the role of wide-bandgap semiconductors in overcoming challenges and shaping the future trends. The session 13 falls on the title Future Trends and Research Directions in Wide-Bandgap Devices. The times to introduce our team chief guest, Mr. Ramkumar. He has accomplished a professional master's in electrical engineering and is doctoral degree at Anna University, Chennai. His extensive experience in designing, analysis, and machines, thermal simulation, and strong focus on renewable energy applications. Mr. Ramkumar had made significant strides in both academic and industry. Mr. Ramkumar has worked at prestigious organizations such as Royal Enfield, Atos Design and Engineering Private Limited. That he has been instrumental in development of electric vehicle motors, controllers, and innovative solutions for various industrial applications. His expertise spans across the software tools like Magnet, MotorCAD, MATLAB, and 6, among others, making him a versatile and knowledgeable professor in his field. In addition to his industry experience, Ramkumar also has made contribution to academic as a senior research fellow supported by CSIR Government of India and visiting faculty at Anna University and esteemed institutions. His research in switch reluctant machines for renewable energy applications is widely recognized and published in international journals and conferences. Ramkumar's dedication to achieve in the field of engineering, his innovation approach and problem solving, and his commitment to renewable energy make him to inspire us all. Now, I request Dr. M. Ramkumar to go ahead with the session. Sir, please.
Yeah. Good evening, one and all, which is participated in this particular event and as well as the particular session, future trends and research direction in WBG. So ultimately, I'm basically an electrical engineer. Okay, so I'm right now working in a domain called electrical vehicle. Okay, so I hope you're able to my screen right, sir?
Yes, sir. It is visible, sir. It is visible.
Yeah. Before starting a session to that, since it's more on academic, people might be attending this. Okay, the industry expectations I would like to stress before starting in this particular point. Okay, I think I'm sitting on the room which is automated lights. Okay, it's getting power off. Maybe I can stop my video. I can start. Okay, so. The particular point what I'm trying to stress to academic people like you guys experts. Okay, so when I graduated, I'm more on to the Powertrains guy. Okay, so which means when I'm studying electrical engineer, I have fundamental things. Then I came to the masters as well as a PhD. Okay, so when I gone through all the academic career in my life, okay, I thought I need to learn in-depth things which is I'm going to study. I want to 100% knowledge at that. Okay, yes, I agree. Industry also looking that who is expertised that they want to 100% knowledge. But industry is not only expecting that. Industry also expert beyond such level. Okay, so what exactly we are expecting? Actually a powertrain guy. Okay, so I'm sitting in Royal Enfield. I'm working for them. So which means my job will be my entire bread and butter will be a motor and controller design and development. Okay, but my company will be expecting only not only a motor design engineer or controller design engineer. It is expecting beyond that, which means when I'm designing a motor, I should not talk about only a magnet. I should not talk about the electrical flux. I should not talk about electrical parameter. So it is also expecting me to talk about mechanical parameter, how aerodynamic should be there, how the structural strength should be there, so how the thermal should be there. So these are the company expecting in your domain itself, which means multi-physics should be come into your domain. That is what additional information company is expecting. Okay. Next to that, When I'm building an electric vehicle, I should know the system to design it, okay, which means which application you are going to design. So say example, you are starting a product which any of the domain. Say example, I'm designing a converter, I'm designing a maybe a, so this converter going to work on where. So why I have to choose a, say example, microchip, why I have to choose a Arduino, why I have to do a DSP based process things. So what is the frequency level expectations? These are the questions to the system level we need to understand, which means any of the design before starting to the particular application, we should understand the design system requirement, okay. So after that only we have to start our product to design towards that, okay. So this is what industry is looking for that. So because why I'm stressing to you guys, I'm a, try to get a people from academic background, okay. So when I'm trying to get an interview of electrical students, they are good in electrical, okay, I agree on that. I'm interviewing on the top in institutions, but beyond that, when I'm asking the question, it is coming as a question mark. So this is what I would like to cover something towards that into the this presentations, okay. So let me go on to that. So as an electrical vehicle, we have a major stages, kind of system level understanding, then how to start a design on the motor and controller, how to integrate with respect to that motor and controller to the your particular vehicle. This is what flow I am having today. So it has a motor, one portion, major portion, and another portion will be a controller, which has a hardware as well as software. Okay. So when I'm talking about initial things, I'm a motor controller designer. I'm not only a hardware person, I'm also the software person, which means I'm building a controller, I'm building an algorithm too. Okay. Which means when I'm designing a hardware, I should not say I'm a hardware person, I don't know the software. You should know the algorithm. Okay, what I'm going to write. This is what a company expectations. So this is what here flow also I can explain to that with a particular thing. In a maybe a modern environment, the electrical vehicle is booming towards like anything. One request to all: if there is any questions, you can stop in between the PPT itself. My request is that. If it is not clear my statement, please also stop me and understand in clear on that particular statement. Okay. So the modern trend to that always when we will talk about non-technical things. When I'm going for the shopping, so when I'm buying a shirt or whatever things, okay. So we will expect something which need to be very good and also so less cost. Okay. So this is a market trends now come into the picture, okay. So we need to produce a very good efficiency but low cost thing, okay. This is what the industry is expecting. And also now electrical vehicle came into the different segment like a scooter, two-wheeler, and as well as car. In a high vehicle also it's came into that. When coming to that, electrical vehicle needs a different level of RPM segment and the high power density, which means, so when I'm talking about high power density, my motor weight should be very very minimal, okay, but it need to be deliver more power. Which means when I'm designing so now right now I'm designing a vehicle two-wheeler, okay. So when I'm designing to the two-wheeler, I have a constraint to the weight because the vehicle weight should not go to that. If I want to push some 100 newton meter torque, I should not design a motor which has a 25 kg, okay. So I should think about that, how compact this overall when I'm getting a target to the system level, they will give a, this is what your system weight should be along with the motor controller, your shaft and gear system. I am also taking care of the mechanical gear system here, okay. So this is entire weight will be given to as a bomb weight. So I have to design and deliver the same spec of the output within the particular weight. So this is what industry is expecting with the compact and good density of that particular things. Second thing, okay. So now when designing a motor, everybody talks about PMSM, IPM, surface mount, axial flux, etc., etc., etc. Okay, but thing is that you should know that where the raw material will be available. Okay, so when I'm talking about raw material in a motor, we have a different material, but the risky raw material is two things. One is the electronics component, second is a magnet. So others can be done, which means iron, silicon, cores, and all we can get a raw material in India. But these two component electronics and as well as your magnet need to be imported into the outside India, and also which is more depends on Chinese market. Okay, this is what entire world is towards that. If China tomorrow is telling my raw material is somewhere in the world, raw material of the magnet will be 94% is available only Chinese. Okay, that domain alone, which means 6% of the magnet material only it's available outside of the China. It's really, it's a pathetic condition for us, which means it will be if Chinese market is turning towards, we will not give a raw material, we will give only a motor. If I'm getting a motor from them, if tomorrow they are saying one motor is X number is increased, we have to listen to them. So that is what people are started now. How reluctance can be used into the motor, reluctance motors, or maybe a ferrite magnet assist motors. Towards that research is going on, which is not established full-fledged, but people are doing, even I am doing on that towards a prototype, which is having a lot of challenges. We are working on it. That is a you know advanced R&D project. This is what I hope your topic to do also. In next generation, what exactly the industry is looking. Okay, so we are looking how to minimize the magnet or how to eliminate the magnet. This is the expectation from the motor. Second thing is minimizing the power electronics component, which is not possible. Definitely we have to work towards that only. Okay, so second thing is sorry, next will be robot and manufacture process. Okay, so when I'm talking about motors, we mainly are using in electrical vehicle two things. Okay, one is a PMSM motor, second is a axial flux motor. Okay, in axial flux motor, manufacture is very, very difficult. We have to do a sintered core pressing, which is very costly, which is not established in India. Okay, so due to that, prototype can be done. But when I want to make a thousands of vehicle in a day, it cannot be. Which means I need to produce a motor for the same. So due to that, axial flux is not developed such a way to produce in vehicle in India. So some of the countries are established. India also is booming towards that. So this is what industry is mainly focusing on, the few points into the motor and controller design. Any questions? Okay. When talking about electrical vehicle, we need to know where I'm going to use this particular motor and controller, or any, when I'm designing, say example, if I'm designing a battery, or if I'm designing a gear system, if I'm designing a kind of a vehicle control unit, or DC-DC converter, or charging unit, anything in an electrical vehicle, when I'm designing that, the requirement should be there. What is the end user application, or what is the end user expectation? Okay, so when I'm doing that, so what is the motor point of view will come, what is the top speed I have to deliver, so which means motor and along with the gear system, so how much speed to the wheel it has to go. If I'm going on that, so what is the expectation incline to the angle, which means, say example, I'm riding in a hill station. Okay, so the same top speed should be attained in 145 in mentioned in the screen. If I want to maintain that 145-degree, if I'm driving in Erkadu or Ooty, that is expectation user or not, that question we need to understand. If I am able to produce, it's good. If you are not able to reduce, the second question has to come. So when I'm designing a maximum inclination, which means some degree angle, so if I'm climbing on that, what is the speed I have to maintain at least minimum? In my product, what I'm using right now is, so we have a 25-degree of the inclination with the 80 kmph I have to climb. So which means there is a limitation for the upper and lower. So you have to design a motor or any device within that. So then we'll come into the acceleration. So when I'm giving a throttle to the motor, which means when I'm making a throttle to the vehicle, how fast it has to attain 0 to 40, 0 to 80, 0 to 100, or 0 to 120. What is the speed expectation from the user perspective? So this is all the product study has to be done before starting the design to the product. So normally any of the OEMs, which means our manufacturer companies, start studying onto the market, what is the user expectation. Okay, so where and all we are going to sell. Say example, in India, the acceleration requirement is something. I'm also making a product for Europe and UK. Okay, when I'm making that, the acceleration requirement of the Europe and UK is something different, India is something different. If I want to make a different product, it's okay. If I want to make a common product for same outside India and as well as India, then the question mark will come. How to change the algorithm for the outside India, how to change the algorithm for the inside India. So which means I have to produce a two software, so which can be maintained in India, one can be maintained outside India. So these are the study we have to make it before starting a design. So this is a interface how I am starting a simulation from the vehicle level. Okay, so we will do a system simulation to understand the requirement of the vehicle. So what is the max torque? Need to get it to that. What is the max power it's need to be? What is the max speed it has to go to that? So kind of study we have to do it for the electrical system. We can have a different set 1, set 2, set 3. If I'm having a this much power, what is the mileage? Say example, if I'm running a drive cycle means the rider pattern. I'm taking a vehicle from Coimbatore, I'm riding towards Chennai. Okay, so this is the things having. So maybe inside city of the Coimbatore, I will write one pattern. From Coimbatore to Salem, maybe in the highway, I will write one pattern. Salem to Chennai, I will write another pattern. Okay. If I'm writing on that, what is the pattern of the user is coming, how the mileage is getting drained. Okay. So this has to be studied into the particular simulation. For that, this is the expectation mileage. This is a battery needed. This is a loss it's coming from the motor. So which will understand the torque speed characteristics of the motor. So this is the first parameter to the motor design engineer. I will tell this is a maximum torque I need. This is a minimum torque in the particular each speed. You can see in my x-axis. So if I'm rotating to the different velocity, so what will be the peak torque condition? What will be the torque condition? This is called NT curve. You might know very well about this. This will be arrived into the simulation. All the industries are depending on simulation aspect. Now a lot of simulation is there into the market. So maybe it depends, industry to industry, country to country, user to user, it will vary, but ultimately behind the reason will be remain same. So we have to arrive from the system what is the requirement of the subsystem. So this is what I'm trying to mention. So if I'm driving a particular pattern, what is the mileage it will come? If I'm riding a, this is called a WLTC. This is outside India. We are following this drive cycle. Inside India, we are following drive cycle called IDC, Indian drive cycle. Okay. So outside India will be WMTC. That will be a motor, world motor drive cycle. That are different drive cycle for different countries where continents we are using. Okay. So we will be predicting if I'm driving this pattern, this is a torque needed, this is a speed needed, this is a acceleration needed. So from that, we will going to the subsystem. So our subsystem will be a motor and controller. Okay. As of now, we saw how into the electrical vehicle, overall the architecture. So what is the electrical parameter for the motor? So these are the three major input will come. So from that, we will be starting that. So this is a high level architecture for the motor and controller. Okay. So the battery system will be there. In a battery system, we will be connecting the pre-charge function, which means we can't start a power supply straight away from 0 to some X voltage, which means I should not power on. It should be very slowly. It has to be go to the system. So that is what pre-charge function will do. So from the pre-charge function, I may have a DC link capacitor. So from that power board will be there. Then low voltage system will be there. The gate driver and microcontroller, all are this. There is a detail drawing is there in backside. So in this, there is a two major aspect we are going to design it. One is a hardware aspect, one is a motor aspect. Okay. So as a designer of the motor and controller, okay, we will start with a controller and a motor. So the steps shown here will be for the controller design, which means we need to know the system requirement. So what is the system requirement? Say example, what is the voltage I'm going to operate? What is the available maximum current? Say example, what is the motor back EMF? This is a, because we faced major things. I would like to spend a couple of minutes here. How the motor characteristics integrated with your controller characteristics. Okay. So when I'm selecting a MOSFET, I selected somewhere maybe I can declare also 150 volt MOSFET, which means the voltage if I'm pushing either forward or backward 150 volt, which means a drain to source voltage. If I'm passing more than 150, it will open out the terminal. So that is called maximum voltage can be pumped. Okay. So when I'm designing a motor, so the X team is doing on a controller, Y team is doing on motor. So what the motor designer is did, he did a back EMF with respect to 175 volt. Okay. So then hardware designer selected the bomb with respect to 150. When I'm running a high speed, my vehicle, if it is getting cut off or purposefully I'm doing a high speed, the MOSFET will be blow with respect to open out. Okay. So due to that, we need to know the system requirement, which means what is the back EMF will come in different speed. When say example 1000 rpm of the motor, what will be the back EMF? Sorry, you are talking about only a high speed back EMF. If I'm able to control that, what is the effect of having a low back EMF, which means 1000 rpm to say example my vehicle is 10,000 rpm. In 10,000 rpm my back EMF is less than 150, your requirement is over. Why you are worrying about 1000, 2000, 3000 and all? Okay, why I'm worrying is the region will come into that, which is regenerative braking, which means we need to create a electrical energy towards the battery when we are not going to functionally as a motoring, which means you know the four quadrant of the motor, right? We need to do a regenerative braking if user is going to touch a brake or he left the throttle, which means I'm going into the downhill, I'm happily leaving the throttle, I'm riding onto that. That time user don't want to push motor action, he want to go smoothly to the vehicle. We can go with a smooth vehicle, but we can recreate the energy, which means reproduce the energy from motor to battery, and we can save some energy towards that. We can increase our mileage. Okay, for that we need to study in different rpm what is the voltage is there, what is the current I can produce out of that voltage. This system requirement has to be studied. Okay, so these are the kind of a system requirement. Then uh, in a hardware aspect it's coming down, so we need to decide the size, material selections, so all those things has to be designed. Okay, when I'm talking about again to the controller, so we should know the our boundary condition of the controller. Okay, so because I faced the difficulties, I was told you have to design with respect to a particular kilowatt motor within particular size, which is not at all possible. Okay, but later we introduced a new technology into that to reduce the size. Okay, so which means this took for a 2 months R&D for us. There are around 40 people sit and doing on the R&D how to reduce the size. Okay, so reducing a 1 mm also it will take 1 day for us. Okay, it's very very critical in industries. When you are doing a project or you are doing a consulting things to the industry, you may not having a major boundary, you have to prove your technology. Okay, so that technology, when I'm getting a limitations like a boundary, this is what dia you have to use, this is what length you have to use, this is what IC you have to use. Say example, there is a term called functional safety. Functional safety means how to protect your control algorithm as well as hardware. So if I want to design a ASIL C, or which also called a missile D, okay, which means the safety of the controller, maybe in terms of I can say cyber security also will come into that. Okay, so when I'm talking about cyber security of the inverters, it's very very complex. Those kind of study we have to make it and go for the study. Then will be a, when I'm designing a controller, obviously it's a basic parameter, thermal study, simulation, all those things we have to do. It's a kind of loop analysis we have to do and get a good design. Once it's done with that, we have to go for the final review and updation. In a final review and updation, what and all we have to do, majorly in a controller we have to do a split as a two major component. One is a HV section, one is a LV section. If it is a LV motor controller, it's okay. One is a power board, one is a controller board. Like that we can split it. In my vehicle I'm using a high voltage system. That is what we have a power board, which is called as a HV section, where the MOSFET, gate driver, all those things will sit. The second thing will be your LV section, which is a controller portion, my microcontroller, my input DC sensor, my kind of sensor control filters, DC link capacitors, all those things will come into that. How to make a design for that, how to make a schematic for that, how to make a Kerber bar that. So we have to have a look into that one by one. We have to verify it. We have to make a prototype. We have to test it. We have to go for it. This is a step we have to follow into the controller design. Then into the motor design, we have to know the again the same validation will come, the system requirement, and to the simulation aspect analysis, then prototype, then calibration of the loop. It- so any system, not only a motor, not only a controller, any system, we have to go starts from the system requirement. There is a simulation. From the simulation, we have to go for a prototype, then prototype to testing, testing to calibration and fine tuning of the our entire understanding. Then we have to go for the again to the design, modifying the design, prototype, test it, and finalize the design. This is the flow we have to make it to the industries. Okay. In a controller, we have to have a design like that. Encoder selection. I hope everyone knows that what is encoder does. Okay. Encoder will be the position sensor for the motor. Okay, which will be near to the motor controller and as well as the motor shaft, which means your motor will be communicating where I'm right now, because PMSM it's not a self-start motor. Okay, which means you have to do two things to start the PMSM motor. We have to do a VD0 and we have to give a three-phase supply, which means I have to make it aligned of the D axis 0. Okay, then if I'm pushing a current, it will start rotating. So that always finding a D axis 0, it's not possible into the market. For that, we have a IC called encoder selection. Okay, which means we have a encoder IC, which is maybe a ABI, maybe a maybe different ICs are there. So we are using ABI things. When I'm using this sensor, there is a sensor limitation is there, which means from the motor shaft, which should be within this distance. Okay, so that has to be ensured, and it has to sense the magnetic flux, which means shaft will have a small magnet. So we have a IC, which is a impulsed characteristics of magnetic flux measurement, that will measure based on the flux flow. It will understand where I'm right now. It will do a PWM switching based on that. So this is the encoder selection. We have to do it very beginning. From that, we have to go for the motor controller selection. Okay. So when I'm talking about motor controller, mainly we have to select the controller microcontroller IC. Okay. So microcontroller IC, when I'm talking about a microcontroller IC, we have a different segment. I have a microchip, I have a TI, I have a NXP, I have a XX market available IC. The first question to the microcontroller selection, what we need to ask is, what is your functional safety level? Okay, on your IC. So what is a functional safety? How it will decide the functional safety? As a technical person, we have to say, what is the switching frequency can be handled by the IC? We have in market K1, K3, like many things. So it will have their own limitations. Maybe 10 kilohertz can be switched. Some of the IC, some of the IC can be handled to 20 kilohertz. Some of the IC can be handled to 30 kilohertz. So when I'm talking about switching frequency, so that will have a different impact into the system. So switching, when I'm doing a higher switching, you will have a higher impact to the ripples, higher losses may come into the your IC. But it will be very smooth, and your DC link capacitance temperature will be very less. So we have to do a DOE, design of experiment. Okay, we have to do it. If I'm using this IC, what are the merits? Which means what are the pros? What are the consecutions? Which means negative, positive. We have to segregate. So we have to segregate. We have to make a DOE matrix. From the DOE matrix, we have to come to the conclusion. If I'm going, these are the major positive towards my application, I can select this. Similar way, we have to select a MOSFET. So when I'm going to the MOSFET, I have to say one thing: is major impact is cost. Okay, I was struggled in the same product. I have a $3 MOSFET as well as $1 MOSFET, which means 100 rupees and 300 rupees. Okay, one MOSFET. So I have a MOSFET which is around 50 MOSFET I'm using into the my controller, which means your MOSFET will be either 5,000 or 15,000, which means my motor controller cost will be changed almost three times only the MOSFET. Okay, so which one you will select? Now when I'm going for the low cost, definitely the compromise will come into the our performance, quality, and the warranty things, which means when I'm producing a motor for the user, he may expect this vehicle will drive without issue for a 50,000 kilometer or 30,000 kilometer or 1 lakh kilometer. So user may have an expectation, company will give some warranty. So normally any of the OEMs now giving a warranty between 30,000 kilometer to 50,000 kilometer for the two-wheeler segments. Okay, so when I'm selecting this component, if I'm driving a pattern which is aggressive, if I'm always driving into the hill, I'm staying on Coimbatore, but my work is in Ooty. If I'm frequently traveling on this zone, your MOSFET always heated up into your vehicle, so it will have an impact into the life cycle. It is going for the worst cycle. Then I have to recreate that into the my design. If I'm always having a high torque peak torque condition or max speed condition, how much life it will come. There is a drive cycle life will be predicted. We call it as a TMDD, which defined as a traction, motor, drive durability study cycle. Okay, which means I have a motor and as well as controller along with the transmission. Okay, all together powertrain, we will validate that. How we will validate that? We have a peak torque, we have a peak power, we have a max speed condition, we have a continuous power. All together we will combine with a particular timetable. We will be running the cycle to understand the particular behavior of the component. Okay, so these are the component selection, which means a BOM selection based on the cost as well as the expectation of the particular things. So once done with that, why I'm selecting this before going for the design, my MOSFET RDS, okay, resistance of the drain and source will vary based on the which product. Okay, if my RDS value is varying, the losses of the MOSFET will be varying. So if losses varies, efficiency will vary. I have to change the filters. Second thing will be ripple. So I have to have a kind of filters before to the drive unit, which means my drivers, I need to add some LC filter or not. Those kind of call I have to take based on the which IC I am going to use it. This is what we are selecting the component. Then we are going for the design. I'm starting analytical calculation, then loss calculation, then filters calculation, then hardware simulation. These are the kind of flow as we seen into the particular previous slide. Like this, we have to go for the design. Okay, in my current architecture or any of the electrical vehicle architecture, as a motor controller we may have a DC input. In the DC input we might have a DC link capacitor to have a smooth interaction between your controller and battery. Also it will prevent your sudden flow on the surges. Okay, so it will impact the ripple as well as your smoothing to the back EMF. Okay, so these are the two things it will create a help into the system. Okay, second thing, we may have a DC voltage sensor to sense what is the voltage is coming. So based on the voltage I can have a algorithm. Say example, I'm operating a high voltage. Say example, my voltage is 72 into the system, which is high for me. I can inject a IDIQ, which is deciding the torque can be very less, which means voltage is high. I can push a less current to produce the same power. If my voltage is getting dropped, which means my power will be reduced, which means I have to inject a little more current to maintain the same power. Ultimately, I have to produce the same power. If voltage is high, I can have a subproduct current will be little less. When my voltage is getting dropped, I have to inject little more current to produce the same output power. This strategy has to be handled by the software. That is what we have to write an algorithm. Normally, I used to segregate IDIQ, which means a direct access current, and indirect, which means a quadrature access current, will be high voltage, mid voltage, and low voltage. I will have a three lookup table into my algorithm. So whenever my system is near to the high voltage, it will take that value. It will be linearly reduced towards my mid value when voltage is getting dropped. So from the mid value, it will go to the linear reduction into the low voltage. So the same IDIQ will be jumped from a second table to third table. That will be handled by my microcontroller. Okay, from the microcontroller we have a gate driver connection. This gate driver will be switched based on my position sensors. Okay, you can have a sensors, the temperature sensor, your voltage current sensor from the inverter. So these are the closed loop system we have to have a reaction for that. So all the reaction will happen based on my throttle input. So we have a different architecture system. My throttle may comes from analog signal, which means straight away as a, you will read a ADC value, analog drive, you will get a value, or you may have a value with respect to your CAN protocol. We have a CAN IC. So from the CAN receiver, we will get all the CAN signal. From the CAN signal, your throttle will come from some X device, which may be VCU, which may be some other interfaces. It will get a analog value. From the analog value, it will convert a digital value to you. It will give a straight away as a signal. From the signal, you have to read, you have to react for it. These are the strategies there in two-wheeler or car segment. It depends based on the architecture. These are the mention I'm trying to mention. In left side, what I'm highlighting here. So okay. So these are the capacitors. You can see the red color which is there here. I have a capacitor things which is connected with the DC link, which means when I'm getting a battery, so I have a capacitors things. I also having the DC voltage measurement, AC current measurement, and as well as DC current measurement. All are ICs with respect to the sensor I have into the LV section board. So my microcontroller, other ICs are sitting into the my LV sections. Okay. So this is my left side product will be, this one will be my LV section. So another one will be my HV section, which means my power board. The power board will be my MOSFET, my gate drivers. So other ICs will be seated. So it can be handled the power things. So it has to be connected together as a separate board. I have it. It should be connected one to one for the communication purpose, for the supply purpose, which means LV section also will be having interaction from your controller board to power board, and the HV section also need to be power transmitted from the LV section to HV section. Okay. So any questions from audience or members? Okay. So we talked about the controller design. Then we will go for the motor design and as well as system next level. So when we are doing this motor design, so
Questions.
yeah,
Sir, we have few questions.
yeah,
Sir,
please.
which is the most commonly used microcontroller for
Hmm.
motor driver application in the industry?
In the industry, we are using K3S32, which is having a capability to handle the ASIL C micro safety, which is there in NXP as well as microchip, which will be approximately our switching frequency is supposed to be 15 kilohertz minimum. Okay, so it should be handled that. That is the expectation. Then the microcontroller IC should be handled ASIL B minimum. This is what standard says. Okay, so based on the standard, we have to select the IC. In Royal Enfield, we are using a ASIL C grade, which is one step ahead from the standard. We are using ASIL C with the 15 kilohertz, which is a K3S32 NXP IC.
Sir, one more question, sir. How does the controller implement various motor control algorithm, example
Hmm.
PID or FOC, at a high level?
There is a industry. There is a two things involved here. Building a base algorithm into the your motor controller now become a common and as well as open source. Okay, so all the microchip ICs, which is microcontroller ICs, all are giving a platform based FOC or your PID algorithms. Okay, which is ready-madely available. From there, we have to just tune it for our motor. Say example, I have a FOC algorithm. For the FOC algorithm, you need to tune your KP, KI, KD values. If you are using a PID controller, if you are using only a PI, you have to use only KP and KI. You can leave a KD. Okay, so that is a depends how overshoot come into the system. You have to tune it. The second thing is your ID IQ value. So then interfaces kind of filters we need to add and we have to close it. Normally, my thing is that in my algorithm I have a FOC with the compiled with the PID.
Sir, one more question, sir. What communication protocols, that is CAN, UART, or SPI, are typically used in motor controller, and how do they facilitate interaction with external systems?
Um, Actually, in a worldwide recognized protocol will be your CAN. Okay, so the CAN 2.1 is a recognized protocol as of now, which is familiar, and also UDS protocol. UDS protocol, it is called also FOTA. Okay, FOTA will be only a software flashing we are using. The communication protocol will be only CAN.
Sir, we can go with the session, sir. Next,
Yeah,
if question arises, I will be just interrupting you.
sure, definitely. Yeah. So next will be a motor design. Okay, pretty. It's my maybe second butter jam came. Okay, which means I would like to say my history, how I came as a motor design engineer. Okay, so the first job for me, writing algorithm for the controller embedded C. I still remember. Okay, so I went to the job. Within 2 months, there is a chance to test it the algorithm what I wrote. So there is a motor given. There is a test bench given to me. The first motor shaft was broken in my first test itself, which means my algorithm frequency it's not synced with the motor. So then my algorithm frequency something different. My motor switching is happening into the some other things. It hit it to the my test bench. It got broken. Okay, this is the first thing. Then I understood I'm not only a software engineer. I should be something else. Okay, so then I started to dig on that. There is a chance came to the from the software engineer to design a PCB, which means it's a small startup company. So within 6 months, I am become a hardware plus software engineer. Okay, so another 1 year, I also become a motor design engineer. This is what my travel came into the motor controller design engineer. So which means this is a flow. When I came to the motor controller engineer, which means entire system, I came to know. Really, I'm requesting all the audience who's sitting here, please teach your students as a system requirement. Please, if say example you are designing a induction machine, so in a induction machines, in the different classes of the duty will be there. When classes of the duty, if it's continuous duty or intermediate duty or whatever classes of duty you are going to define, it has to be changed their design. So when you are designing a induction machine, you may have a V3F, which means variable voltage, variable frequency drives nowadays, because most of the industries are automated lines, which means our manufacture lines are used by induction machine, but along with the V3F, which means variable voltage, variable frequency drives. So when he is designing a motor, he should know about the drive. He can't talk about only I am a motor engineer. I will not talk about my mechanical design. I will not talk about my thermal design. I will not talk about my controlling algorithm. Really, it's not fair. Okay, so that is what when I'm starting a motor design. See here, I'm also should have a characteristics of the motor. If the same motor acting as a generator, that's what. Now PMSM, you should do a motor and as well as a region. Region is nothing that generator. Okay. So how to act as a motor, how to act as a generator, you should know that. When I'm doing a writing algorithm, so when I'm pushing a negative torque to generate a particular regeneration, it should be very smooth. It should not harm to the rider feel. When I'm injecting a negative torque, it's nothing that you are stopping your motor. Say example, I'm running on some 70 newton meter condition. I'm pushing a 70 newton meter against to that to produce a region means it's really wrong. Okay, so we have to push, which is not going to affect to the rider feel. We have to slow down the speed of the vehicle if he's not giving the throttle, but you should try to create a power out of that. So this is a logic we have to hear. So when I'm starting a design, I should know the motor characteristics. I should know the generator along with inverters and control logic. This is what I'm telling. So why I'm talking about analytical calculation, which may be Excel, which may be a MATLAB, which may be a 1D simulations. There is a professor called DJ Miller. Okay, I hope everyone knows. He wrote books also. He made a excellent software called Speed. Okay, SPEED, speed software. So this software will create within 2 seconds the entire motor design. If you are giving the limitations of the particular, say example, this is my L by D ratio, this is my power requirement. So what is the probability of the slot pole combination? What is the probability of the motor characteristics? So the same characteristics we can compare with the different motors. Okay. So when I'm talking about I want to particular torque and speed, which motor you want to design? Second question will come. Sir, you want to either it's maybe a BLDC, it may be induction machine, it may be a reluctance machine, it may be a DC machine. So XX machines are there into the market. How to decide them? Which motor I have to design? So this particular platform will help you. If I'm designing a this particular motor, what is the bill of material will come? Bill of material is nothing that your rotor core, how much weight will come, my housing, how much weight will come, how much magnet weight will come, how much length will come, how much width will come, the entire characteristics of the motor you will come to know. So how I can go for it? So when I'm doing a particular initial design of the island fill, I came to the conclusion for my design, my BLDC, nothing that which is called a PMSM, concentric winding. Okay, so PMSM originally it will be a distributor winding, but in EV industry we are using a concentric winding. This is combined between BLDC and PSM, PMSM characteristics. Okay, and axial flux having the major advantage out of this particular things. Okay, which means when I'm proceeding to the next stage, I propose to my higher management, sir, either I will go with the PMSM or I will go with the axial flux. These are the merits, these are the demerits of the both design. So when I'm proposing that, I'm not only a person going to decide the design. So my manufacturer guy will come, my quality guy will come, my testing guy will come, so my system guy will come and sit, and also battery and other subsystem guys will come into the picture. So those will ask their requirement, which means from the battery, if I'm asking, I want 500 amps current, he will not going to give to you. My limitation 100 amps, 200 amps, 300 amps. He will tell that within the particular parameter I'm able to produce or not. Then my mechanical designer will come. Sir, my vehicle environment this is. For your motor, you can have this much size. So this kind of limitations will come. In the limitation, which machine going to adapt for it? So second thing, when I'm talking about this machine, either you are going to have a forced cooling or natural cooling, which means either you are going to design only a fins of the motor to cool your motor, or you are going to have a forced cool, either oil or water or particular X material of the things you are flowing into the motor thing, you are getting cooled up. Okay, so these are the question will come into the picture. So based on the system requirement, we have to take a call which motor we are going to do. So this particular interface, normally we used to do with respect to script. This is what I learned in life. Writing a Python algorithm for this particular um, design flow. See, I'm a motor engineer. I learned a motor software. I learned a hardware. But writing a Python is out of my scope. Okay, so which is nowhere linked for me. But as an engineer, I started a software engineer. So I learned a Python also. I'm writing a code for Python. Okay, to optimize or minimize my workload, or to make it my system very faster, which means the faster environment what industry is looking, the user has to do or employee has to do all the things very fast, giving a output very fast, but stabilized manner. So when I'm going up fast, I should not have a something wrong. For that, you have to write some algorithm or software. Maybe right Excel micros. So when we are having a Excel, so Excel itself will do a lot of calculation for you. If you are writing a backend formulas of the motors, so you will ask some X input. From that, you will derive the output. Similar way, MATLAB also. So kind of things you can write and you can interface with respect to software. All the software having in which is available market, the Python is a language can be integrated, which means any of the software will be optimized based on your, say example, I like to maybe a later stage I will show video. No, I will now itself I will show, since we are talking about this. Yeah. see this particular video. So when I'm changing this panel, okay, so what are the input? I'm designing a machine with respect to slot pole combination. I'm going to the particular model. I'm changing particular value. You see, the entire model will be getting updated from the stator. So to the my given value. Okay, this is not a inbuilt software characteristics, which we have to make it to user fast. For example, I'm designing a 3D model of the particular motor. If I want to design, it will take a 2 to 3 days of the particular slot pole combination. Again, I want to try different slot pole combination. Can I try for it means again I have to take it 2 to 3 days, which is industry will not allow you to take it. For that, we wrote a script along with my team. So when I'm having a particular requirement from the current design, if I'm changing a particular length or particular slot pole combination, can I run the simulation? Yes, we can do, which is will make a very fast to you to proceed further. And also you can have a DOE, design of experiment. If I'm doing this, this is my output. If I'm having this combination, this is what expectation. If I'm having a stack length of X, Y, Z, what will be the result? So this kind of iteration can be done not only analytical simulation, also can be done in a 3D simulation. Okay, so this is a normal industry practice for the people. So once done with the particular design iteration, you have look into that. We run a simulation. You see, n number of iteration tried. In the n number of iteration, there is a one place came near to my requirement. Okay, these designs are going to help me into the further level, which will be happen within half an hour. That is more important. I was tried everything simulation in the platform of the speed software to conclude in half an hour. So I try to say example 1,000 design. Out of 1,000 design, I'm going to pick only a 10 design. Okay, in the 10 design, I can further investigate. I can shortlist a number of design. Okay, so this will make you to very faster things. You can see here I'm getting a efficiency map. I'm getting a speed torque characteristics. All those things. From that, I can conclude my design. Okay, once done with the 1D simulation, we will moving to the 2D simulation. Again, if you are doing, you are not convinced with your particular model, we can do any of the model which is designed in the previous 1D platform. Okay, so here we can study a temperature, flux density, or demagnetization effect. I hope everyone knows the demagnetization. Okay, so magnet, if you are say example, I'm using a SH magnet which will withstand 150-degree. If I'm using a UH magnet, it will withstand 180-degree. If I'm using a UH plus some additional material, it may go to 200. If I'm using a EH magnet, it will be a 240-degree. These are the different magnet. When I'm using this magnet, if I'm motor is getting heat up beyond the particular temperature, so the magnet will get demagnetized. Or in a magnet into the motor, if it is getting a eddy current loss between the magnet, it may also lead to the demagnetization. So these are the things you have to study and understand as a field study. So field, we are talking about B, magnetic flux density, magnetic intensity. So your flux of the heat flow, thermal heat flux, magnetic flux, all those things we can study. We can understand that how it this motor going to get a or the study will be happen into the particular platform. Sorry. Once done with that, we will be moving to the multiphysics simulation, which is called 3D. Okay, so sorry, before moving to that, we may also having to the 2D platform drive cycle means different speed torque characteristics. You can see in this particular, if I'm changing it continuously with respect to first 1 second, I'm running with a particular speed, particular torque. Second curve, I may have a different profile. If I'm running like this, how much time it will run to heat up the maximum temperature? Say example, I have a cutoff at 190-degree into the motor. In 190-degree, to run this profile, how much cycle it has to go. Say example, I'm starting a vehicle from Chennai till Vellore. If I'm going to the max speed continuously, how much temperature will come? It will reach or not? Those kind of question will be answered by the simulation. So we can go for the detailed study as well as. Once done with this particular study, we can go for a 3D model integration or system integration, where we studied the vehicle level things. We can pull all the motor design to that. We can run once again. We can understand all the characteristics are fulfilled or not before making to the prototype. So 3D simulation, it's really a tough, or it will be help you to understand the major impact, like each corner of the motor, entire 3D model we have to study and get the feel of the particular design. So you have to understand the different aspect. This is what the video I shown to you as a 3D model. Any questions on the simulation? 1D, 2D, 3D?
Sir, no, sir. We can move
Yeah.
forward.
So next will be a multi-physics. I will show on this video, which is separately there. I'm using a older version of the PPT, so that will not available in this PPT. That's what I'm having a separate file for it. When we are talking about thermal study, we need to understand how much. Say example, if I'm running a air-cooled motor, so after reaching some X kilometer, maybe a 100 kilometer or 200 kilometer, my vehicle is will get a cutoff. This user will like or not? This question will come. If user will not like, sir, I'm basically from Bangalore, so I'm starting from Chennai, from here 350 kilometer. So I don't want to stop in between. I have to go for a single ride. Your vehicle able to provide? This is a question. If requirement comes, we may go for the cooling technology, which means there is another oil system. The oil will be pumped into the motor, either housing or shaft, different duct system are there. We can have a forced cooling to the system. We can extract the heat from the motor out. It can be run little more distance to run for the distance. So these are the study we have to make it. Either it's a conventional cooling or forced cooling. If it is a conventional, it's a air. If it is a forced, we may have a air forced, we may have a oil or water jacket. So different cooling technology are there to incorporate and study. These are the study we have to make it after the simulation. So the flow will be 2D simulation, extracting the loss. From the extracting loss, we should know the thermal analysis. If thermal analysis is temperature is heating up too much, have to go for the design change. Can I change the thickness of the fin of the motor from some 10 mm to 15 mm or 1 mm to 2 mm? If I'm making a kind of change, what will impact? So if my temperature profile is good, okay, there is no impact on my first design. If I'm reducing a fin size, it will reduce my BOM cost, because I'm going to use a aluminum housing or particular compact, costly material. So if I'm using a kind of reduction into the size of the housing fins, can I go for it? So next will be, if it is oil cooled or water cooled, I'm pumping with respect to 10 meter per second, liter per second, or whatever it. So 10 liter, if I'm pushing, the temperature is so good. Can I reduce the flow to 10 to 8 or 8 to 6? What will impact? If the flow is not sufficient, we have to increase and see. These are the simulation iteration has to go before making to the prototype. You completely understood, okay? So this is the characteristics of the motor. These are the variations of the my design. So from this variation, we can understand the entire capability of the particular design. So this all will be virtual, no cost for that, which means all the industries having the simulation software, then they are producing the particular simulation results. From that, they are going for the particular manufacture things. Okay. Now we are into the system validation. We made a particular motor, we made a particular controller, we made a particular hardware, so we made a particular cooling technology. We understood entire motor controller. Sir, I made it so good, sir. My design is giving you a 99% efficiency, or even you imagine that 100%. It will not possible. 100% efficiency. So my job is not done or not? No, your job is not done. You have to prove when you are putting your system on your design, it's going to work or not. Because say example, I made a motor, When I'm going to connect with my gear system, it is not going in, which means my sprockets are not in line with the design, or my mountings are not okay, or my algorithm where I communicated the CAN protocol, the CAN is not getting a proper information from my vehicle control unit or my battery system. What you will do? Nothing to do. It will not even run into the system. So when you are talking about only a efficiency of the motor, you may get it 95% if you are doing a good integrated motor control. The maximum 94 95 we can achieve. Okay, uh, any power rating I'm talking. Okay, so if you are having a better design and thing, but when I'm putting into the vehicle, it may vary of your efficiency because our drive pattern will be varying. Okay, so you should understand that as a system level how the loss will going to happen. So our motor, inverter, controller, so all the losses. My MOSFET will have a losses, my motor will have a losses in the motor, stator coil, stator core, rotor, magnet, my bearing. Okay, it'll also come into the picture. Friction loss will be there, windage loss will be there. In the different losses, we can understand as a system before manufacturing. Any questions, sir?
No, sir. No, sir. We can start, sir.
Yeah. So these are the flow we have to make it and understand the system. My motor is okay or not, which means you can see my motor pulled into the particular system, entire electrical vehicle, which has a battery, which has a gear system, which has an entire thing. I will pull into the design to the particular system level. I will do a simulation. My motor is going to give a sufficient validation or not. So this simulation can be carried like this. So we can produce the drive cycle. You can see when I'm driving at different time with respect to different kmph. So what is the losses is coming? How the torque is produced? So how much efficiency is there? So this can be predicted before manufacturing of the particular motor itself. So which means my complete validation virtually varies. If you are a good designer and good understanding between you and tool, the variation of the simulation and prototype not more than 5%. I almost 10 years I'm into the market, so I never see a variation from the simulation. If I did a 3D model, I'm talking about 3D model. 1D model will have a accuracy of the 80% to the prototype. 2D model will have a 90% accuracy of prototype. Your 3D model will have a 95% of the accuracy of the prototype, which means if I'm going to declare to my management, sir, my motor will produce 100 Newton meter and a particular 10,000 RPM, it will at least produce 95 Newton meter, 9,500 RPM. Okay, if that confident comes to your simulation tool, so they are happy because you are not wasted any of the materials, you are not spend much time to the market. Okay, you run a very fast simulation, you came to the conclusion, you are proceeding. So this is a flow we have to make it to the any design. Analytical, then analytical to 2D, 2D to thermal, thermal to 3D, 3D to system validation. So it's a motor or controller, both are same. So this is a flow we have to make it. I would like to show one video. I missed it here. See how the visual happen. So how much temperature will be there in the temperature, how the flow will be there in a different location of the motor. So how the temperature, you can see the blue portions, red portion, green portion. This will be indicating you to how much temperature in the particular design. Okay. Okay, I think I'm done with the presentation. Now we can ask the question if you have anything.
Participants, the session is open for the questions. I request the participants to kindly share the questions in the chat box.
Sir, I hope there is no question, sir. Thank you for accepting our invite, sir. It was really a nice presentation, sir. You have given an overview of what you're doing in the industry and some of the results which we can't do it, but you have shown it, which was really useful for us. And I hope it will be just creating some knowledge to explore the things. Thank you very much, sir. Thank you for
Thank
your
you.
time.
Yeah, thank you, Onandal, who's there in a particular meeting. So the last request is please focus on multi-physics. This is the one line I'm trying to stress. Okay,
Sure, sir. Sure,
so
sure.
don't limit yourself as an electrical engineer. Please come out from that and understand the entire market. Work with all the departments, which means all the physics.
Sure, sir. We will be.
Thank you all.
Participants, I have posted the feedback link in the chat box. Just I will be showing what you have to do during your test session. Just I will be sharing my screen now. I'll be sharing my entire screen. Okay, I hope the screen is visible. I'm just going to one of my colleagues' portal. I hope you are able to see the portal. I hope you are able to see the portal. In the portal, you can see the cursor. You can just see the cursor. Participants, kindly mute your mic. You can see my cursor. Participants, kindly mute your mic. You can see my cursor. Okay, in the cursor, I have just in the left side of the window, I have chosen assessment. I have chosen assessment. If you are clicking the assessment, I hope the test link is active here. You can just click the test link. The instructions will be given. The instructions will be given here. 25 questions in 45 minutes. So by clicking the checkbox, if you are just pressing the start button, it will be starting by 6:30. It will be starting by 6:30. It has been mentioned here. You can take the assessment at or after 6:30. Okay. So this is one point, and another one is the certificate will be generated only once you are completing the assessment and also when you are putting the feedback. Okay, same way towards the left of your window you will be having a feedback below the assessment. Okay, if you are clicking the feedback, if you are clicking the feedback, I hope you can see this February 17 to 17 2025 to February 22 2025 semiconductor. In that you can see there will be a red color with a message box, submit feedback for FTP bar workshop. Okay, if you are clicking that, you will be shown with a feedback. After completing the feedback and after completing the assessment, I hope the certificates will be generated for you. Okay, I will be sharing. I hope everyone would have seen the attendance. If there is any query, you can just post it in our group itself. I will be rectifying it. I invite you all for the validatory section. Kindly connect for the validatory session by 7:30. The session is open. Just it will be for 15 to 20 minutes. So I hope everyone will be able to join by 7:30 for the validatory session. And open feedback session will be there with the management team. Thank you very much for 1 week patient listening to the faculty development program. After completing the assessments, I will be just noting down how many members are completing it. uh, I will be just insisting in the group and also in the teams. I will be active in the team. If you have any doubt, you can just contact me. Just now I'm stopping the sharing. I hope everyone is clear how to take the assessment and how to
Y-
post the feedback. Any questions?
No, sir. Yes, sir.
Yes, tell
Everything
me,
is
ma'am.
clear, sir.
Okay, ma'am. Thank you. Thank you very much, ma'am.
Thank you, sir.
Excuse me, sir.
Yes, sir. Yes.
My question is that after attending the assessment,
Okay.
must have to give feedback, and then
Yes, sir.
only
Yes.
the is generated, na?
Yeah.
Okay, fine.
Sir, you have 1 hour time is there, sir. 45 minutes will be for the assessment, and 15 minutes you can complete the feedback, sir. I request everyone to join for the validity session, sir. Thank you very much, sir.
Yeah, definitely. Okay, it sounds good.
Thank
Yeah.
you. Thank you, sir. Thank you.